Instead, for this, I just kind of went the shorter videos, so we'll see what we think. So we kind of group planets by these planets, Sun, these planets, the asteroid belt, and these planets. Okay, they kind of have, they're kind of grouped together. We call these guys the terrestrial planets. Okay, sometimes they're called the inner planets, but sometimes the inner planets are actually, what two planets are closer to the Sun than the Earth?
Mercury and Venus.
Mercury and Venus. Sometimes those are called the inner planets. I don't know. Okay, so the terrestrial planets. So all planets, terrestrial planets, okay, and these, what do we call these planets? Do you remember?
Oh, sorry.
Jovian or gas giants, they kind of have a couple of names. Jovian planets, gas giants, yeah. They all went through this kind of what we call planetary differentiation. It's a favorite term to put on a unit exam because it just rolls off your tongue. Planetary differentiation. And when I think about planetary differentiation, I think about Italian dressing, Italian salad dressing. It's totally planetary differentiation. Because Italian salad dressing has your, like, you have your oil and your water and your vinegar. Now, vinegar and water will mix. They're miscible. But oil and water and vinegar do not mix. So oil would kind of form. Does oil float or sink? I think it floats. I think it floats. So oil floats. Okay. And the reason that oil floats on Italian dressing is because it's less dense. Okay. When we talk about the density of something, we're saying, like, when you look at kind of it's the ratio. When you look at how much mass there is per volume, there's less mass per volume for the oil than there is for the water. The water is gram-packed, more dense, okay, more mass per volume. So planetary differentiation, all it is basically, you have to kind of think about what we talked about on Wednesday, okay? Starts with I'll call it the solar, and then it starts with letter N. What do we call this? That kind of our star and the planets form from?
Nebula.
Nebula, perfect. Solar nebula, yes. So during, and it would take like 100,000 years or so, every star, kind of takes about this similar thing to go from a nebula into a star system, a star with planets, okay? So about 100,000 years, basically, matter is gravitating towards the center, but like we saw Wednesday, we also kind of have these tracks of material. Starts with the letter A. What do we call it when a planet kind of gets bigger? Accretion, yep. So we have these planets accreting. Now, as the planets accreted, they took kind of rocky material, and how does this work? It was kind of, they actually heated because of gravity, okay? Just kind of like the sun heated, but they also heated, remember with the moon, we saw that it was heated from the interior by, what do they call it? Radioactivity. Just kind of elements kind of being somewhat radioactive and decomposing, okay? So you've got to think of these planets as kind of being a little bit warm, okay, as they kind of got bigger and bigger as they accreted. So with that warmth then, there was a bit of what I call ooey-gooeyness. And with ooey-gooeyness, just like your salad dressing, you could go ahead and have ooey-gooey, heavy things sink, and ooey-gooey, lighter things rise. That's planetary differentiation in a nutshell, okay? So our sun turned on about 4.6 billion years ago. That's when it began going blue. And when I do that, I'm talking about solar wind. The only way you can have solar wind is if you begin in generating its own energy. So, do you remember how it generates energy? How does the sun generate energy? Nuclear fusion. Nuclear fusion. Yep, that's how the sun did that about 4.6 billion years ago. And with it kind of cleared the way of the kind of the cloudy sort of stuff with the lighter stuff that hadn't formed into a planet. That was kind of cleared away. I saw those in the figures on Wednesday. So we talked the other day about tsunamis. Well, just briefly touched on tsunamis. And tsunamis actually are a result of, these are two plates on the Earth's surface, plate tectonics. So we can kind of have plates go like this. We can have plates separate. We can have plates come together. Okay, all sorts of options. And as they come together, they can both go up like that, or one we can have a subduction zone, that sort of thing. So, but the reason plates can move like that is they have a liquid underneath it. Okay, they have a liquid mantle underneath this, generally what we could call the lithosphere. Lithosphere plates going on a liquid mantle. So not all planets have that ooey gooey liquid mantle. Well, we're going to see that here in a minute. But we say if a planet does have liquid for the plates to move on, we say that that planet is geologically active. So we're going to see the terrestrial planets here in a minute, all compared. I know, and then we're going to switch gears to Mercury. But I want to take a glance at all of the terrestrial planets, all of the inner planets, including the moon. And you're going to see with planetary differentiation, you have heavier things sinking to the core. So we have iron and nickel in the core. You can see it's kind of a gray color. And then we have the mantle. Actually, there's a solid part of the mantle and a liquid part of the mantle. It's a little bit lighter. And then our crust is the lightest. So you'll see kind of color-coded on these structures. So it looks like this from left to right. Now from left to right, you're going to see the biggest getting smaller, getting smaller, getting smaller. So you see the gray, that is our core. There's a movie out there that's kind of cheesy, but it's the core, it's kind of fun. Then that we have this big orange part is your mantle. So we actually have solid mantle and liquid mantle. And then this kind of tan part is your crust. So that would be the lightest material. And I don't know if you remember, but when we talked about how our moon is composed, it actually, because planetary differentiation of the Earth had begun, the moon does not have much of this. It has a lot of this. Because remember that the moon came from the Earth and planetary differentiation had already begun. So there's the Earth. Now, there's Venus, so we're going down in size. We're going to see here in a minute that actually Venus is geologically active. There's Mars, size-wise. What do you think Mars is relative to size to the Earth? Volume-wise. Yeah, it's about half of it. Mars is a lot smaller. When it comes to kind of having an analogous planet to the Earth, actually Venus is more of kind of a sister to the Earth than Mars is, in part because of its size. Okay, so what planet are we missing? Mercury. So, oh my goodness, what do you think? What would you say about Mercury's core? It's really big. It's like oversized. Yeah. What about Mercury's size? It's small relative to the Earth, isn't it? And then just for kicks, here's the moon. And I kind of said that the moon has an extra dose of kind of these lighter elements, like the mantle and the lithosphere, than it does the core. And that makes sense. So this is where I like to say, like, if you have a pizza at home, okay, Papa Murphy's, we're kind of like Papa Murphy's things. So you take it out of the oven, and you have your family size pizza right here. Just my husband and I, we still like family size. so here's your family size. Now, let's go ahead and it's piping hot. We're going to take one piece of pizza out, and we're going to put it on a paper plate, and the rest we're not going to close the box. We're going to leave the box open. Okay. And then we're going to come back in 10 minutes. Which pizza is cooler? The one that's by itself or the one that is kind of still in a circle? Which is cooler? The one that's by itself. And I mean, that makes sense. It's like you got a little more surface area, you got less heat within that. So yeah, it's going to cool off. And that's what planets did. So of course, Mercury is the smallest here. Mercury is the smallest, and so it cooled off the fastest. You might say, well, Mercury's the closest to the sun, but it still cooled off the fastest. And with cooling, actually, then what was maybe ooey gooiness, Mercury has no ooey gooiness. So as it turns out, Mercury, because it's small, cooled off quickly, And although it may have had plate tectonics in the past, Moon. Earth, definitely with regards to geological activity, yes. Venus, yes. Mars? The time I was putting this together, which was a few years ago, I was like, I looked and looked and looked, and Mars is, the jury's still out a little bit with regard to Mars. So geological activity. Okay, now we're kind of just going to go through, it's going to be like you get out the album and you talk about your kids. We're going to talk about our planets. We're going to pick them apart, you know. So we're going to start with Mercury. To me, and sometimes I turn this into a test question, does Mercury, and I'm going to show you some more pictures of Mercury, does it look like the moon? The surface of Mercury looks like the moon, I think. So this is the first of a few videos. I think it's maybe 4 minutes or so. Slides. This is Mercury. It's showing you kind of the highlands, like the moon has highlands. It's in red here. The lowlands, mare, what we call the moon, are kind of blue here. And I mentioned Messenger is the spacecraft that's taken a lot of these pictures. So again, you can kind of see, actually it's hard to make out, but this is a famous feature of Mercury called the Caloris Basin. Wait, no, Caloris Basin. And the cool thing about the Caloris Basin, you can't get a sense of this with this photo, but it's humongous relative to the tiny planet. And another cool thing about the Caloris Basin is that this is the impact crater, but over here there's like, at the time of the impact, it was so energetic that it kind of jumbled. It created this kind of weird looking thing on the opposite side of Mercury. One of the features that Mercury has are called scarps. So here's a picture of a scarp. I don't know if you can kind of see this little ridge right here. And I mentioned that Mercury's like your single piece of pizza that cooled faster than the other planets just because it had less mass. And as it cooled, it's kind of like around here, your sidewalks kind of do funky things when they kind of expand and cool, expand and cool. That's why sidewalks, they're segmented to kind of give you some expansion and contraction. But sometimes they just, scarp is like a sidewalk kind of.
Is that what Mercury does? It heats and cools.
This scarps would have been formed, well, it was a little bit, but scarps would have been formed as your single piece of pizza kind of turned to, think of scarps not being formed anymore, but when it turned to stone, your piece of pizza you don't want to eat anymore. Basically, as it did, let's see, as it gets cool, it contracted. So as it contracted, it formed these kind of ridges. Now, the video talked about, I think I have it coming up here in a slide, but the Mercury, oh man, didn't it say something about 3 months later you'll get into nighttime? So it rotates so slowly. It's like see, it goes counterclockwise, right? So Mercury rotates so slowly. It's kind of like if you go to Walmart and they have those rotisserie chickens, okay? It's kind of like on a rotisserie chicken that's like, and this side burns, and this side never gets done. So Mercury is just terrible. One side is really hot, and the other side is really kind of cold. So, and that's because it rotates so slowly. Poor thing. Okay, so I have some interesting facts. Let's take a look. It's another video. I think it's about 10 minutes. Interesting facts about Mercury, and then we'll see what they didn't cover. Let's see. I wonder. Maybe. Where'd my slide go? Oh my gosh. Okay, there we go. All right, so what do I got? They didn't mention anything about the polar regions having solid ice. They talked about the Venus's atmosphere. Very slim. I have up here no permanent gaseous atmosphere. They said it's a very thin one. Let's see, atmosphere. Down here kind of talked about the fact it doesn't have an atmosphere, and when we talked about Venus, Venus has a very thick atmosphere. Actually, that's kind of why it has those crazy temperature swings listed here. And then this last one here is the fact that now, okay, so now I am the Earth, okay, and we have Mercury and Venus there. When I go to, let's look at it this way. That's my daytime Earth. This is my nighttime Earth, right? Does this make sense? I'm never gonna see Venus and Mercury. I'm never gonna see them up there, okay? Because they're inner to me. My best bet of seeing those planets, which are inner to the Earth, is gonna be kind of, and there's this thing called greatest elongation. Basically what a greatest elongation is if I from Earth look, there's the sun, the biggest angle that it is in the sky, that's greatest elongation of either Mercury or Venus. So if that's the case, if it's over here and we call this the kind of the configuration, we call this is if I'm the Earth and this is Mercury or Venus, then when I'm going to see it, it's going to be as I spin my daytime spin, my rotation on axis, I'm going to see it close to the sun, either near sunrise or sunset. And greatest elongation is the best. And I know if you're like into, I bet, in astrology, that sort of thing, the greatest elongation is like one of those configurations they kind of focus on. So they are like that. Let's see what we can do with Venus. Shall we? Maybe. Okay. It is right here. So I have a little video to watch for Venus too. Maybe right there. Now, Venus were taken, I think it was 1981, by the Soviets, who successfully got through those clouds they were talking about in the video, landed on the surface of Venus, and I think I probably mentioned it sent back some pictures before it died. The thing about it is that little spacecraft was under not only the sulfuric acid, you're like, but it was also under a lot of pressure. I can't remember what it is, but we're under about 1 atmosphere pressure. If you're walking around, and literally it's a gas pressure, you can think of it as kind of a, like this, or just, anyway, it's a gas pressure. It's like 9,000 times that at the surface of Venus. So Venus is a tough nut to crack. The thing about it is it's very glowy. It's very striking. In the morning sky right now, like I was saying, Venus is out, gosh, I don't know, maybe like about 45. And again, I talked about greatest elongation. I don't know when that is, but it's very bright because of its clouds are very reflective. This is a picture of Venus. The best thing we've done, you're going to see actually artist renditions of what the surface of Venus looks like. And what they did was they took an orbiter and they had it do like radar images, send down a signal, get the signal back, and get the topography of the surface like that.
Is it just the pressure that's stopping us from going there? I mean, is it really, really hot there? I mean, I know it has the atmosphere, so it's kind of blocking it, but is it really hot?
You know, I'm curious as to why we haven't been back too. It's pretty hot. Did they say like 900 degrees? And I don't know if that's degrees Celsius, I assume. It's very hot, but at high pressure. But I'm kind of curious why we haven't been back.
I mean, would the pressure be too much for a human?
For humans, yeah. Humans can't. We don't have the technology to have a man on there, or woman on there either. But we do have the technology, I would think, to send another probe to land on the surface. That's kind of weird. Well, I'm going to start with this because I think I need to delete these pictures. All right, my picture went away. But so I'm going to start with this slide on, so we're not going to get through Venus. We'll take a running start at Venus on Monday, and then we'll go on to Mars, and we'll see how far we get what that all looks like. It's pretty cool stuff. Yeah, and get some labs done this weekend. Tonight's supposed to be nice.